Hey, it's Jim, and this is FRM Part 1, Book 2, Quantitative Analysis, and the refresher exam. Staying in Chapter 3, now we're on pages 30 and 31. We have a regional bank, 50 loans, past 3 years, total of 9 defaults, average of 3 per year. Loan defaults for this bank are independent events. That's probably important. Distribution is skewed. That's probably important. Identify, all right, so we have two questions. The type of loan default distribution, so look down there. We just talked about the binomial. Remember the uniform distribution, that's a continuous random variable occurring with equal probability, right? The Poisson distribution, that models the counts of events over fixed time periods. The exponential distribution, that models the time until the next event. All right, so based on that, you probably came up with the correct answer already, the Poisson distribution. But identify the type of loan default, we did that, and the probability that 2 defaults will occur during the upcoming year. So here's a good old formula for you to memorize. I teach this in my derivative securities class as well. And so notice what we have down in the answer explanation. Rare events, there's the independent, Poisson distribution has skewness in it. And the one parameter is lambda in there. So there's the equation. You feel free to pause and get out your calculator. And so you get 22.4%. So I'm guessing that that GARP, it's tough to say what they're likely to ask, but here, what we've done in this question, this is not a likely question on the exam, but there maybe are 2 or 3 embedded questions inside of this one. All right, on to hypothesis testing. 66 clients, unique positions in the alternative investment asset class. Test the performance of each client's portfolio in relation to that of equities. Substantial position in hedge funds, but layers with commodities, derivatives. Oh, rare wine and whiskey bottles. Stamp collections. All right, let's see. Computes a mean annual excess return of 2.3% in excess of the benchmark. Standard deviation is 3.9. State the null hypothesis and determine if the excess returns are significant at the 95% level of confidence. All right, so we're going to have to do a couple of things here. First is to figure out what that null hypothesis is. So if we're doing this test, we probably have an equal sign, and so the alternative is probably unequal sign. So it's got to be either A or C. And are we going to reject the null or fail to reject the null? Well, we need to go ahead and get out our test statistics. So it's down there on the right in purple. So we're just going to put that 2, 3 in the numerator, subtract out the 0, and then divide by the standard deviation. And of course, we need to adjust it for the square root of n. You remember all that stuff that you read about in the chapter. And so what do you get? 4.79. So that's greater than 2.0. Now note, we've got 66. So that's, the t. Remember, the t statistic goes up to, essentially 30. And then when you get to infinity, then it becomes the z-score. So here we just said it's greater than 2. So if you want to go to the table, and, maybe GARP will give you a partial table. So it might be 1.96. But I always remembered those numbers, 2. So there you go. Therefore, reject. Which statement is most accurate? What do we have? Snack food industry, regression parameters, standard errors, and t-stats. All right, so we've got an alpha and a beta. There's our estimate. There's our standard deviation. So that t-stat, the orange column there, that's just purple divided by, what is that, navy blue or dark blue. And then there's an r squared. All right, so the intercept term is statistically significant. Well, it's 1.05, so that's probably right out. Remember, just use the general idea of about 2.0. The slope term is statistically insignificant. Well, it's 6, so there's no way that that's not significant. So A and B are right out. Correlation coefficient, 629. Well, the correlation coefficient squared is 629, but not the correlation coefficient, which means that D has to be the correct answer. So we figured that out. Go ahead and pause the video and make sure that you can do the math down at the bottom. But notice that there are 4 potential questions inside of just this one question. Moving on to stationary time series. We've got an analyst collecting data on a golf club manufacturing firm's revenue and income levels of country club members. AR model is appropriate, but the analyst suspects the revenue time series to be non-covariance stationary, but the income level to be covariance stationary. Now remember that for covariance stationarity, you only have to worry about 2 moments, the mean and the auto covariances. Remember earlier on we had the table with the first 4 moments. You only have to worry about 2 of those here. The analyst is aware that to be covariance stationary, the mean and variance and auto covariance must not change over time. That's one of the important assumptions. But also remember, the mean has to be constant, the variance and the auto covariances have to be finite. Remember that. We don't put that in here, but that's probably important to remember. If the analyst is correct, she is likely to conclude the mean of the revenue is 0. Well, I'm not quite sure we can make that conclusion, but remember the mean has to be constant. Partial autocorrelation is a linear transformation. And then D, partial autocorrelation is a function of the revenue. Time series shows a 0 drop-off. All right, so those partial autocorrelations, remember those are nonlinear transformations, so B is out. And there's a really good picture inside of this chapter. It doesn't have 0 drop-off, which means it goes straight across. It has a substantial drop-off. It maybe drops to close to 0. So B and C are out. The auto covariance of the income time series depends on the covariance of successive income data points. So that's what I was saying to you earlier about the mean and the auto covariance. So there you go. All right. Pursues complex option pricing strategy, purchasing and writing call options. Some market data is available but limited. Seeks additional risk management tools to help him. Most concerning is the magnitude of the variance of the estimate for the individual call options. To improve the accuracy, the investor will most likely use, well, let's think about this. To improve the accuracy of the estimation, we're probably, and remember the chapter is called simulation, so we're probably going to do some kind of simulation. Remember that law of large numbers? So wouldn't it be awesome if we could just simulate and simulate and simulate? But that's, takes a lot of time, takes a lot of money, takes a lot of resources. So we have these 2 things that kind of streamline them. We have the antithetic variance and the control variance. And the big difference between the 2 is the antithetic variance. These things have negative correlations with the observations inside of the simulation. The control variance, they have a mean of 0, but they have low correlation. So I think I answered the question then. Which one do we like? We like A. So A, control variance have a mean of 0. Yeah. High correlation. So that throws B out. Why don't we like C and D? They have a mean equal to the mean of the original distribution and will be effective only if their correlation with the input variables equals 0. No, that's not true. They have to be negative, and so that's the same answer for part D. Not less than 1, but less than 0. So remember that the control variance, they've got lots of correlation with the observations or with the simulation, and then the antithetic, they have negative correlations.